Normally it's not so loud. Okay. Now you can't hear it at all. Okay, let's get started. Just a reminder about the tour of the cyclotron that we're going to do, not this Friday, but the following Friday, November 6th. It's going to be instead of class, so we're not going to come here on that Friday. I'll tell you how to get up to the lab as we get a little closer. As I mentioned before, cameras are okay, and some of you have done this already, but the rest of you who need to, please send me an email today. If you're not a U.S. citizen, please just let me know your nationality. Again, it's information the lab requests before they give us access. Okay. So what we're going to do this week, and probably not all of the week, is Chapter 5, and then we're going to quickly move on to Chapter 6, because we're going to lose a couple days of class, one with the tour, and then the following Friday with the exam. So we're going to go a little fast over this material, and you'll see that there isn't that much material in these couple chapters. So today we're talking about the interaction of radiation with matter, and I just remind you of the homework assignment I gave out on Friday. I'm going to go in slightly different order than Lily does, but we'll talk about all the topics that he has there. And so what I'd like to talk about first, and unfortunately my display is not working properly today for reasons I don't quite understand. Let's see if I can fix this. Function F8. Okay, so maybe I'm just going to do it this way. If this is a problem, let me know, but I'm having trouble getting the whole display on. So let's first talk about the way gamma rays interact with matter. We spent a lot of time discussing where gamma rays come from, the nuclear processes that are responsible for them, and I've shown you spectra that we've measured from various gamma ray sources, but now the question is, what is it that's going on with gamma rays in terms of how they interact that allow us to detect them or to use them for various applications? And so there are three basic processes by which gamma rays interact, and they're shown on this first slide. And at any given time, 1, 2, or 3 of them may be going on, and we'll see how we decide which is the most important in a few minutes. So the first one is called Compton scattering, and it's a process in which a gamma ray, shown here coming in from left to right, scatters off an atomic electron. So what we imagine is we've got a gamma ray going into some material. That material is electrically neutral. So we've got neutral atoms, and that means we've got nuclei with bound electrons attached to them such that each atom is electrically neutral. So what happens is a gamma ray comes in and bounces off one of those bound atomic electrons and transfers some but not all of its energy to that electron. And so the electron gets knocked out of the atom, it escapes, and it carries away a certain amount of energy. And because not all the energy of the original photon got transferred to that electron, a residual or secondary photon goes off that's labeled as gamma prime in that drawing. And the probability for this interaction depends on the energy of the gamma ray and the angle at which the secondary photon is emitted. And also the energy of the outgoing photon depends on the energy of the incoming gamma ray and the angle that it's emitted. And we'll go into more detail on Compton scattering in a minute. A related phenomenon is called the photoelectric effect. And here the idea starts out the same. You have a photon hitting some material. Again, they're bound atomic electrons. But what happens in this process is the entire energy of that photon is absorbed by a single bound electron. And that electron then comes out of the atom with a single energy. The energy of that electron is the energy of the incoming gamma ray minus whatever binding energy that electron had. And that's a function of what element the electron was bound to and which of the atomic orbitals the electron was in before it absorbed the photon. So these two processes are related, but notice that here there is no secondary photon because all the energy is carried away by that electron. Whereas here, you've got a recoiling electron and a secondary photon. This process is actually the one for which Albert Einstein won the Nobel Prize. Most people think he got it for special relativity, but in fact he never got the prize for either special relativity or general relativity. In 1905, he published 3 incredibly important and famous papers, one of which was special relativity, one was on the photoelectric effect, and the third was on what's called Brownian motion. and each one of them was worth a Nobel Prize in physics. But relativity was still considered to be quite controversial, and so in 1921, the Nobel Committee awarded him the prize, but they gave it to him for the photoelectric effect. And they told him that in his acceptance speech he shouldn't say anything about relativity. He talked about it anyway. He knew it was right. He knew it was right. So that's the photoelectric effect. And then the third process by which photons interact is called pair production. And this is a process in which E equals mc squared literally happens. Okay, so you have a photon coming in, and in the vicinity of a nucleus or an atom, it converts itself from being a photon into an electron-positron pair. Okay? Now this can only happen for photons that have an energy above twice the rest mass energy of an electron, which means the photon has to have an energy greater than 1.022 MeV for that to happen. What you'll discover if you try to go through the kinematics of trying to conserve energy and momentum, and you have to do this relativistically because we've got energies which are larger than the rest mass energies of the particles we're talking about. This process cannot happen in a vacuum. So a photon traveling along in free space cannot just spontaneously turn into an electron and positron. And what you'll find when you try to do the calculation is you can't conserve energy and momentum if you start off with a particle that has zero rest mass and turn it into particles that do have rest mass. So this process has to happen nearby some other object. So if a photon is traveling through material, there are atoms and nuclei there. What those atoms and nuclei do is provide a mechanism that allows energy and momentum to be simultaneously conserved. Essentially what happens is the photon comes in, and in the vicinity of the nucleus gives it a little kick, so the nucleus recoils with a small amount of energy but a reasonably large amount of momentum, and thereby allows energy and momentum to be conserved. So that's pair production. And in general, all three processes will be going on if we're talking about a photon that's above 1.022 MeV. If we're below that, then it's only these two processes which matter. So let's talk a little bit more detail about Compton scattering and go through the kinematics here. So this is an expanded view of what we just saw. So we have an incoming photon whose energy is labeled E gamma, an outgoing photon whose energy is E gamma prime, and then the scattered electron. Lily just labels this electron momentum as P. I've tried to be a little more specific and call it P sub E. And if you think about the momentum, these are vector quantities. We need to conserve the momentum. So the original momentum of the photon, which is labeled P gamma there, must be equal to the vector sum of the momentum of the outgoing photon, P gamma prime, and the momentum of the scattered electron, P. And now what we want to do is conserve energy and momentum. So we can calculate the kinetic energy of that recoiling electron. It must be just equal to the difference in energy between the incoming photon energy E gamma and the outgoing photon energy E gamma prime. And now, in general, I need to do this using special relativistic mechanics because I'm going to talk about energies which are comparable to or greater than the rest mass energy of the electron. So all of this is going to use special relativity. I can't get by with classical mechanics here. So what that means is the kinetic energy of the electron is the difference between the total energy of the electron, the relativistic total energy, and its rest mass energy. Okay? And then I go back to this drawing and use the law of cosines to relate the momentum of the electron and the outgoing photon to the momentum of the incoming photon. So I take PEC squared, which is just relativistically equal to the difference between EE squared and E squared C to the fourth. And I use that triangle to say that's equal to E gamma squared plus E gamma prime squared minus 2 E gamma prime cosine theta. That's just the law of cosines. And then with a little bit of algebra, I can solve for E gamma prime in terms of E gamma and the angle at which the photon emerges, the secondary photon emerges. Okay? So what sets the scale for the energy transfer is the electron mass because everything's scattering off the electron. And the energy then depends sensitively on the angle at which the outgoing photon emerges. Okay? So that's the Compton scattering formula. these are some bubble chamber images of the other process going on. This is pair production. And so what happened here was this is a bubble chamber. It's a chamber filled with liquid helium or liquid argon, something like that. There's a magnetic field which is going into the board, and there was a source of photons up at the top. And occasionally what happens is a photon comes in, and remember, in these kind of images, the only thing that produces tracks that you can see are charged particles. So you don't actually see the photon coming in, but right here, what seems to have happened is it converted into electron-positron pair. And so one of these is the electron, and the other is the positron. They bend in opposite directions because they're opposite electric charges, and there's a magnetic field into the board. So they tend to curve in spirals. So that's one pair production event. Here's another one right here. What seems to have happened there is, again, the photon came in, and right here it produced an electron-positron pair, and here's another electron. So what happened is it happened right near the vicinity of an atomic electron. It knocked that electron out of the atom and produced that track, but it also produced the electron and positron. Okay, so these are the kind of images you can see of pair production. And in this case, the source of the photons is relatively low energy. It's a few MeV. And so the only kind of particles that can be produced through this mechanism with that energy are electrons and positrons. But if you had a higher energy source of photons, say they were 10 GeV photons, then you can produce any kind of pair that you'd like. You could produce a proton and an antiproton, for example, and the tracks would look similar. Okay? So this process of pair production, we normally talk about only applying to the production of E plus, E minus, and that's true for the things we're going to talk about here. But at higher energies, any kind of particle-antiparticle pair is possible to be produced. So now if you look at how these photons get absorbed as a function of their energy, this is a plot out of Crane's book where he's showing you the photoelectric cross-section, that is the probability for the process to happen. This is being plotted in lead as a function of the photon energy. And what you see is, first of all, the cross-section or probability for that interaction falls rapidly as the energy goes from 0.01 to 1 MeV. That's a general feature of the photoelectric effect, is that in general, it's most important at low energies, and it falls off as you go to higher energies. The scale of this would change for different materials, but the general shape would be the same. And then in addition, you notice that there are these notches and peaks. So there's one right here at about, 4 or 5 keV rather, another one around 15 keV, another one around 100. Any idea what those notches and peaks have to do with? This is lead now we're talking about. So remember what's going on here. The photon is coming in. This is the photoelectric effect. So the photon is coming in, giving up all of its energy to one electron. Okay? Those electrons have very specific binding energies. Okay? If I'm in the 1s orbital, if I'm an electron in the most tightly bound orbital, in lead, that orbital is bound by something like 80 or 90 keV, 80 or 90,000 electron volts. And so if I'm a photon coming into lead, if I don't have an energy greater than 80 or 90 keV, I can't undergo a photoelectric effect on that electron. So when I have 80 or 90 keV, I can be absorbed on that electron, and the cross-section gets very, very large, and then once I surpass that energy, it keeps on falling. So each one of these notches and peaks corresponds to a particular binding energy of an electron in lead. So these are the 1s electrons, these are the 2s electrons, 3s, and so on. And if you go and look in the back of the table of isotopes, for example, there are tables that show you where these binding energies are for all the elements. And so you could predict ahead of time where these notches and peaks are going to be. And they'll be at a different energy for each element. Over here is a plot showing the relative contributions of the three types of interactions for photons as a function of their energy. So this is the gamma ray energy running this way. This is the Z of the target. And what it's trying to show you is that at low energies, it's mainly the photoelectric effect. That's what we're seeing over here. In the middle, meaning somewhere between, let's say, 100 keV and a few MeV, it's mainly Compton scattering. And then once we get well above the threshold for making an electron-positron pair, then the pair production becomes more dominant. Okay, so if you're trying to figure out which of the processes are most important, the first parameter you want to look at is what energy photon are you talking about. At low energies, it's going to be mainly photoelectric, as long as the energy of the photon is above the binding energy of some electron in the material you're talking about. Okay? Again, if you had a 10 keV photon and you were interested in doing the photoelectric effect on a K electron or a 1s electron in lead, that's not going to happen. Okay? Question? Yeah.
So you're saying that very high energies can produce any kind of pair.
Yes.
So what determines what kind of pair you're going to produce?
So it's going to depend on the nature of the particle you're trying to produce and what interaction would be required to do it. So for example, suppose I wanted to make, let's say, a W plus and a W minus boson. So the W plus and minus are the particles responsible for the weak interaction. So that would be a weak interaction process to produce them. And the weak interaction by its nature is going to have a very small cross-section. So while it's theoretically possible, it's very unlikely for that to happen. For the example I gave before about making a proton and an antiproton, that's much more likely to happen as long as I have sufficient photon energy. That would be a strong interaction. And that in fact does happen and has been observed. So it'll be different for each process and it'll depend on the type of particle you're talking about. There's always going to be a kinematic factor which will tend to favor the lightest mass particles, because for any given photon energy, I will have more final energy available to produce a light mass particle than a very heavy mass particle. And that phase space factor will also be a contributing element in figuring out the relative rate for each of them.
Does that mean it's really unlikely to produce like an tau or an anti-tau?
Yes. Very unlikely, but nevertheless it can happen. Right. And it doesn't have to be just by pair production via photons. A related process, since you're asking about this, is you can take, okay, it's not going to do that, huh? Okay. They're making it hard on me. Okay. Okay. So you can take an electron-positron and combine them. Well, there used to be a working accelerator over at Stanford which did this for a living. And what happens is you bring the electron and positron together and they annihilate. And of course you can get two photons, but in addition you can get any pair of particles you like. And so what they would see is things like mu plus mu minus coming out. This is actually how the charmed quark was discovered, because what they made is a charmed anti-charmed pair in exactly that collision at Stanford. And so these all happen, and the relative probability depends, like I said, on what kind of interaction is responsible, the masses, and lots of other factors, but you can get any old pair coming out. Okay, getting back to this then. Okay, so photoelectric, Compton, and pair. Now, next week I'll bring in some detectors and we'll start looking at how this manifests itself in terms of what we actually observe. But this is a kind of energy spectrum that is typically observed in a high-resolution germanium gamma ray detector. So the idea here is you have a detector which is made out of germanium. It's sensitive to photons, and the idea is you have a source of photons, gamma rays, which are hitting this detector, and you measure the energy signal that the detector observes, and you end up with a spectrum that looks like this. So this is the energy that the detector sees, and this is the relative probability of the detector seeing that. And what you're doing is you're sending in exactly one energy photon. So if you had a perfect detector, the detector would end up measuring exactly one energy, okay, the energy that you're sending in. And this peak out here is called the photopeak. That is, it's really shouldn't be labeled that way. It should be labeled as the full energy peak, because that is the energy of the photons we're sending into the detector. But let's assume for a minute that those photons had an energy on the order of 1 MeV. Is it likely that that peak is produced by the photoelectric effect? No. According to that diagram I had a minute ago, for around a 1 MeV photon in most materials, Compton scattering is actually the most likely thing to happen. So this peak is not produced by the photoelectric effect, at least not initially. In addition to that photopeak, what you see as I move down in energy is, first of all, a gap. There aren't any events there. And then I see a kind of step and an edge. And then let's just concentrate on this continuous distribution first. It's a smooth distribution that starts at this thing called the Compton edge and goes all the way down to 0. That's the primary way these photons are interacting in the material. They're undergoing Compton scattering. Okay, so the photon comes in, it bounces off an electron in the detector, the electron recoils and produces a signal that the detector registers, and then a secondary photon is emitted, which usually does not interact in the detector, and so if the original energy was here and you measure an energy over here, that means you lost the difference between this energy and the one you measured. That was the energy of the secondary photon that was emitted. Okay? And if you go back to this Compton scattering formula that we had up here a minute ago, you can calculate the fact that there is a maximum energy that the recoiling electron can have for a given energy incoming photon. That corresponds to when the photon gets backscattered. So as you might have imagined just from classical mechanics, that if the photon comes in and the secondary photon goes in the backward direction, meaning 180 degrees, that transfers the maximum amount of energy possible to that electron. And in that case, the electron would go off at 0 degrees relative to the incoming photon direction. And what that means experimentally is that for a given energy photon coming in, the maximum energy I can give to that electron in a single Compton scattering is right here. And there's a gap in between the full energy and that, which you can determine from that formula. Okay? So a single Compton scattering can't produce events very, very close to the full energy peak. As the photon angle changes, we get various amounts of energy deposited, and that's what gives rise to that Compton continuum. And the Compton edge corresponds to that maximum energy I can give, corresponding to the 180-degree scattering of the photon. Now, what are these guys? Okay, these are labeled single and double escape peaks, and the idea here is that this photon actually has more energy than needed to create an electron-positron pair. So the photon goes into the germanium, and inside the germanium, it produces an electron-positron pair. The electron and positron come to rest and deposit all their kinetic energy in the detector, and then eventually the positron finds an electron to annihilate with. And so this process happens inside the detector, and generally the annihilation happens with the electron and positron at rest. So these two photons each have 511 keV of energy. Okay? And this is happening inside a relatively small crystal of germanium. So here's my electron, here's my positron. The positron annihilates. I get two photons which have to go off back to back. And since the detector is fairly small, there's a relatively large chance that one or both of those photons will escape the detector without interacting. Okay? If one of them escapes, I get this peak, which is exactly 511 keV below the full energy peak. And if both of them escape, I get this peak, which is 1022 keV below the full energy peak. And so if I have a high energy photon in a germanium detector, typically this is the kind of spectrum I see, with all three processes going on. And you might wonder, well, how did I get this full energy peak if he's telling me that it's mainly Compton scattering? So what happens is I can't get anything in here unless I have more than a single Compton scattering, and occasionally I will. Occasionally the secondary photon that got produced in that first Compton will get captured on another electron and either undergo another Compton scattering or a photoelectric effect. And through a combination of multiple Compton scatterings followed by a final photoelectric effect, I generate that peak. Okay, so there's a lot of physics going on in those spectra, and I'll bring in a detector next week and show you this. Okay, so much for photons. Let's now talk about electrons. We talked about beta decay, we talked about internal conversion, so we know that there are lots of sources of electrons, and now we're imagining that we have such a source, and we're shooting electrons into some material and asking how they interact. Now, what's one of the major distinctions between electrons and photons? They have mass, okay, so that's going to play a role. And another major one? They have electric charge, right, okay. So they have mass, but in terms of atomic or nuclear masses, their masses are still small. And so now imagine you've got an electron coming into some material, it's got an electric charge, and so it will interact with the first things it sees, which are going to be other electrons. Okay? As it's going through the material, the electrons are orbiting the atomic nuclei. The incoming electrons don't really see the nuclei very much because those nuclei are surrounded by atomic electrons. So the electrons will interact via the Coulomb interaction. That's a 1 over r squared force, so it has a very long range compared to the nuclear force. And so the electrons will interact with other electrons via these Coulomb scatterings. And since an electron is scattering off another electron, these are equal mass particles that are interacting. What that means is the electrons can suffer very large angle scatterings, and as a result, their paths are very erratic. Okay, so when I shoot an electron into a material, it doesn't travel in a nice straight line because it's bouncing off electrons, and you get a very smeared track as the electron penetrates through the material. So that's one way the electron loses energy. As it's going through the material, it's scattering off electrons, and it can transfer energy to the electrons. It costs a certain amount of energy to kick an electron out, depending on how much binding energy it has, but that energy comes from the kinetic energy of the incoming electron. So ionization produced as a result of these scatterings is the major energy loss mechanism for electrons in materials. Another process for electrons is something called Bremsstrahlung. It's a German word that means breaking radiation. And what happens here is the electron is traveling through the material. It's slowing down as it's losing energy. And you know from classical electromagnetism that when a charged particle accelerates, it produces radiation. And that's what Bremsstrahlung is. So the electron is coming in and slowing down very, very rapidly in the material. And because it's being accelerated, in this case decelerated, but nevertheless that's an acceleration, it produces photons. That's what Bremsstrahlung is. And this tends to be most important for high energy electrons and in materials that have a high Z. So in things like aluminum, Bremsstrahlung is not so important. The collisions with electrons will be the dominant way the electrons lose energy. But in something like lead or gold, Bremsstrahlung will become relatively more important. And so the rate of energy loss, the rate at which the electron slows down and loses energy, is a complicated function of the kinetic energy of the electron, the Z and A of the material, and the density of the material that it's traveling through. And here are some plots showing the energy loss, or what's called the stopping power, of electrons in aluminum and lead. And what's being shown are the two different contributions. The solid lines are the contribution from electrons colliding with electrons and losing energy. And just to be clear, this is the incoming electron energy here, and this is the energy loss in some what appear to be funny units. It's often written as dE rho dx. So dE dx is the specific energy loss per unit length the electron travels in the material. So the units might be MeV per millimeter or MeV per centimeter. In order to compare materials that have very different densities, you multiply x by rho. So this is the density of the particular material. So for lead, something like 11 grams per cubic centimeter. For aluminum, it's something like 2.7. And then this product of the density times the distance comes out to units of grams per centimeter squared. So it's a measure of how much material the electron traverses in order to lose a certain amount of energy. And the upper plot, as I said, is for collisions of electrons with electrons. And you can see there's not an enormous difference between the energy loss of electrons in aluminum versus that for lead when you make this correction for the density. Okay? And that is the dominant loss mechanism for electrons until you get to very, very high energies. The dashed curves are the energy loss for this breaking radiation or Bremsstrahlung. And you can see at low energies, let's say in MeV, the collision with electrons is by far and away the more dominant. As we get to higher energies, and especially for a high Z material like lead, you can see that the Bremsstrahlung begins to compete. And it's still higher energies. The major way the electron will lose energy is through Bremsstrahlung. Okay? You can take the energy loss and integrate it, basically, figure out how much material an electron has to travel through before it gives up all of its kinetic energy and comes to rest. And that's what we mean by the range. So the range is the distance that any kind of radiation has to travel before it loses all of its energy. And the plot showing the range in units of grams per centimeter squared. So again, it's the physical thickness of the material times the density. So it's a distance times a density, which would be grams per cubic centimeter. So the units of the range would be grams per square centimeter. And this is being plotted as a function of the electron energy for aluminum and air as the two materials that the electrons are traveling through. And so if I wanted to know how much aluminum do I need to stop a 1 MeV electron, I can try to read that off here. So here's 1 MeV, and I want to read off how many grams per centimeter squared that is. And that's going to be the upper plot. So it's going to be, I don't know, half a gram per centimeter squared, roughly. Okay? And the density of aluminum, I said, is about 2.7 grams per cubic centimeter. How much material am I going to need? A fraction of an inch, a quarter of an inch or so is plenty to stop a 1 MeV electron. And if you remember from a demonstration I did the first or second day with an electron source and trying to stop it, it was a quarter of an inch of aluminum that we used to pretty much stop the electrons. Okay? And you can see that in these units of range being expressed in grams per square centimeter, there's not a lot of difference between air and aluminum. But the density of air is enormously small compared to the density of aluminum. So it's not going to be a quarter of an inch of air, it's going to be a very long distance of air to stop that 1 MeV electron. But the integrated amount of material along that trajectory will be very similar in terms of grams per square centimeter. Okay, so now we're moving our way up. We talked about photons, we talked about electrons. Now let's talk about heavy charge particles. So now what we're talking about are things like protons or alpha particles or neon nuclei, something like that. The reason we talk about this is, one, we have radioactive sources that we know emit alpha particles, and so we can get alpha particles hitting various materials, and we'd like to understand how they. And we also have accelerators that can produce beams of any particle we like, and we'd like to understand what happens when those particles interact with matter. So again, thinking back a little bit, we went with photons, which had no mass and no electric charge, to electrons, which had a small mass and an electric charge. Now we've got very heavy objects. These are thousands of times heavier than an electron, and they have varying amounts of electric charge depending on what species they are. So let's think first about what happens if an alpha particle goes into some material. And imagine it's an alpha particle that was produced by some radioactive decay, so its energy might be on the order of 5 MeV. So it's going into my block of aluminum or lead or whatever it happens to be, and the first thing it sees are electrons. Again, because the electrons are surrounding all the atoms there, the alpha particle has 2 units of electric charge, and so it interacts via this long-range Coulomb interaction with the electrons. And if I look at it in the laboratory frame of reference, I've got essentially stationary electrons sitting there and an alpha particle moving in with some kinetic energy and some velocity. For analyzing this, it's better to change to a reference frame riding along with the alpha particle. So I get on top of the alpha particle and I run along with it, and what I see in that reference frame is an electron coming at me. Okay? And since I've transformed from a reference frame in which the alpha was moving with a velocity v alpha that way to the reference frame in which the alpha is at rest, I see an electron coming at me with a velocity v alpha. Okay? And now this is a situation that I would say is analogous to a BB, the electron, hitting a bowling ball, the alpha particle. Okay? It's a very light particle coming at me, the electron, and a very heavy particle, the alpha particle, which is on the order of 10,000 times heavier than the electron, so that's not such a bad approximation. So if I have a BB hitting a bowling ball, what's going to happen? If a BB hits it head on, what's going to happen to the BB? It's going to bounce straight back with the same velocity it came in with. And what's going to happen to the bowling ball? Essentially nothing. I mean, to first order, nothing. It's going to sit there. You're right, to conserve momentum, it has to move a little bit, but in this approximation, it sits there. So the electron in this case, which is my BB, bounces straight back with the original velocity it had. It doesn't really lose any energy in that process. Now I transform back to the laboratory frame. Okay? This was all in the reference frame of the alpha particle being at rest. Now I jump back to the lab frame, which means run that way with a velocity v alpha. So in that reference frame, the electron moves with a velocity 2 v alpha. Okay? It's a simple way to understand that the electron recoils with twice the velocity the alpha particle came in with. Okay? So how much kinetic energy does it have then? Well, the kinetic energy is a half me twice v alpha squared. I'm assuming I can use non-relativistic kinematics here, and it turns out it's okay because the alpha particle velocities are very low. And so if I plug in the numbers, the kinetic energy the electron gets then is 4 times the mass of the electron times the energy of the alpha divided by the mass of the alpha, and that ratio over m alpha is a very small number. So if I have a 5 MeV alpha particle coming in, the kinetic energy that the electron acquires is 2.7 keV. Okay? A very tiny amount of energy gets transferred in the single collision of an alpha particle with an electron. And that's just because the mass of the alpha is so large, it really can't transfer very much energy to such a light object. Okay? But that's a typical kind of energy loss for an alpha particle in a material. And what that means is if I'm going to stop this alpha particle and bring it to rest, it takes thousands of collisions for this to happen. Okay? As the alpha particle or a proton or a deuteron or whatever traverses a material. Now again, because I've got a heavy particle, proton, alpha, whatever, and it's interacting with very light particles, electrons, these heavy particles tend to travel in very straight lines. Okay? Unlike the electrons, which I was talking about a minute ago, which, because they were scattering off of equal mass particles, could undergo very large angle scattering. So the heavy particles travel more or less in a straight line. And then there's a very well-defined range, which is the distance that needs to be traveled for the particle to lose all of its kinetic energy. And that range depends on the kinetic energy of the particle, the type of particle it is, and the material. And so this is a cloud chamber image taken of tracks produced by the alpha decay of polonium-210. So this is a little petri dish, basically, with a vapor of alcohol in it. And when a charged particle traverses through that, you get tracks produced, little droplets of alcohol condense. And so each one of these is a single alpha particle decay. And you can see this source produces one energy alpha particle. They're about 5.3 MeV. And you can see that the length of these tracks are all very nearly the same. And they're very straight lines, indicating that the alpha particle went through the cloud chamber, lost energy in a very continuous way through scattering off electrons, and produced very straight tracks that all had about the same length. That's characteristic of heavy particles in any kind of material. And there's a formula, which we'll see in a minute, for calculating the range or the energy loss of particles in a material. Once you figure that out for one material, it's relatively easy to figure it out for other materials using the so-called Bragg-Kleeman rule, that the range in one material is related to the range in another, and it basically depends on the densities of the two materials and the atomic weights of the two materials. Okay? This is a very empirical relationship that was discovered. If you want to know more quantitatively how to calculate the rate at which a particle loses energy in any material, the formula was worked out in the 1930s by two very bright people, Hans Bethe and I've forgotten Bloch's first name, but Mr. Bloch. And it's called the Bethe-Bloch formula. It's a formula which we're not going to use very much, okay? But the point is to understand the physics here. The idea is you're shooting a projectile into some material. The projectile has a charge ZE, so it's a proton, it's Z is 1. If it's an alpha, Z is 2. If it's a neon nucleus, then it's Z of 20. And it has a certain velocity, V, which we can relate to the dimensionless quantity beta, which is V over C. So V is beta times C. It's the velocity of the incoming particle. And then these other quantities, which all have the pluses on them, have to do with the nature of the material in which the ion is going. This is the target material, the density, and the atomic weight of the target material. The formula then says that the rate of energy loss is this complicated function of all those quantities. Okay? And that tells you how much energy is lost per unit length or per unit mass per unit area that the projectile traverses. So this is called the energy loss. And then if you integrate that, if you integrate the energy loss from the initial kinetic energy the particle had when it entered the material until it stops, that's what we call the range. Okay, so the integral of d dx dE from the initial kinetic energy down to 0 is the amount of material it takes to stop that particle. And again, it depends on the nature of the particle, its energy, and the nature of the material in which you're shooting it. Okay? And these are plots of the range for various types of particles in various materials. So each one of these curves is for a different projectile. These are alphas, these are protons, these are, alphas and protons in different materials, lead, copper, aluminum, air, and so on. And this is the energy of the incoming particle. And so if you want to know how much material it's going to take to stop a particle, you can read it off a table like this. So for example, if we go back to something we had a minute ago, we were talking about electrons in aluminum, and we were trying to figure out how much material it took to stop those electrons in aluminum. Now let's suppose I have a 5 MeV alpha. Okay, so I want to read off this plot, which you can't see very well. This is the energy scale for alphas. I want to come over here to about 5 MeV and try to read off this curve, which is this one for aluminum, alphas in aluminum. So it's going to be that one, and it's going to be up here somewhere. And this is the alpha range. So what am I going to need? I'm going to need something like 2 milligrams per square centimeter of aluminum to stop a 5 MeV alpha. Okay? That's a much smaller amount of material than I needed to stop that 1 MeV electron a minute ago. And remember again from the demonstration I did, it only took a single sheet of paper to stop the alpha particles, where it took that 1/4 inch of aluminum to stop the electrons. And that's what these curves are telling you quantitatively. Okay? And those curves are generated simply by integrating, not simply, but by integrating this expression. So I think you have a homework problem that's going to force you to go through that once, but I'll show you how to do it in a quicker way in a little bit. Because the important thing is to understand what the physical parameters are that are going to matter, not so much that formula, but it's useful to be able to calculate these things. So this shows the rate at which these protons, for example, are losing energy in aluminum. And so here what you're doing is you're shooting protons of various energy into aluminum and using that beta block formula to calculate the energy loss, the amount of energy in MeV per gram per centimeter squared that the protons traverse. You can, and this is plotted against the proton kinetic energy. At low energies, the energy loss is very, very high. As the proton gets higher and higher energy, the energy loss falls off. And if you go through the beta block formula, you'll see that's exactly what's expected. So low energy charged particles will lose a lot of energy. Relatively high energy particles will lose a smaller amount of energy per unit length of material they're traversing. Okay? And that's true for any charged particle. It's just being plotted here for protons. If you then use that information to say, okay, I'm riding along with one of these protons and it's going through some, how does the energy loss change as the proton loses energy? So it's starting off, let's say the proton's coming in here, it's traversing my block of wood, let's say, and as it's going through, it's losing energy. So as it moves in this direction, its energy goes down, and therefore its rate of energy loss goes up. And that's what this curve is showing you, that the amount of ionization, which is what the proton is doing, because it's knocking electrons off of material, increases as the proton gets deeper and deeper into the material because the proton's energy is going down. It reaches a maximum right near the end of its range, right near the end of its track, and then it falls to 0. Okay? That's a very characteristic kind of energy loss curve, again, for any charged particle. And this peak over here is called the Bragg peak. It's the place where the highest energy density is created along the track. And again, it goes back to this other curve, which says that the energy loss increases as I get down to low energy, and that's right before the particle comes to rest. So most of the radiation dose or damage is done right near the end of the track. And this kind of shows you a comparison between electrons traveling through material and some heavier charged particle. This is alpha particles, but the same kind of plot could be made for protons or anything else. So this is the relative intensity or the number of particles as a function of the depth inside the material. And what you see for alpha particles is their number remains more or less constant until you get right at the range, and then they fall off dramatically to 0. And that was reflected in that cloud chamber image I showed you of the tracks of the alphas. They travel a very well-defined distance and just stop. Whereas electrons, because they're bouncing around in random paths, have a much more diffuse range. It isn't as well-defined for electrons. And so for a given electron energy, you don't see a nice sharp cutoff, depending on exactly the trajectory the electron takes. For these heavy particles, we can make use of that. For example, later on we're going to talk about radiation therapy as a way to treat cancer, and I mentioned one example of that last week when we were talking about boron neutron capture therapy. The boron neutron therapy is a nice technique, but remember, you have to get a boron-labeled compound into a person, and that isn't always possible. So another way to do a similar job is to take an external source of heavy charged particles, like an accelerator, and shoot a beam of those particles into a person, and arrange the nature of the particle and the energy such that the particle comes to rest exactly where the tumor is. And this is a plot of this kind of thing. So this is a measure of the relative dose, or the amount of ionization that's being produced, as a function of the depth inside of an object. Okay? And what's being compared here are 3 different types of radiation. We've got gamma rays, which we talked about earlier. They interact via the Compton, pair production, and photoelectric effect. They provide a dose which really doesn't change a whole lot as a function of depth inside the object. Neutrons, similarly, but look at this. This is nitrogen ions. So imagine you had a source of nitrogen ions at relatively high energy, such that they could actually get into a tumor, let's say, on someone's kidney. Okay? Because of this beta block formula, as those nitrogen ions are traversing the body, they lose energy continuously, but the bulk of the energy that they have is deposited right at the end of their range. And so if you figure out how deep you have to go into that person, pick that energy just right, you can deliver the bulk of the dose right to the tumor and hopefully destroy it and leave the surrounding tissue pretty much untouched. Whereas with these other kind of radiation, you're not specifically delivering the dose to the place you want to. Yeah?
Is that the only type of radiation that has a peak in it, even over like long ranges?
So this is true for any heavy charge. What I mean by that are nuclei. So protons, deuterons, alphas, and anything heavier. They will all have a similar shape.
Of the nitrogen? Or
Of the nitrogen. It's more pronounced for the heavier the ion. So for a proton, it wouldn't be quite so peaked. For an alpha particle, it would be a little more peaked. And as you get heavier and heavier, it gets more peaked. But they all look similar to that. Right? And so at Lawrence Berkeley Lab, they used to have a cyclotron. It was called the 184-inch cyclotron. And it delivered a beam of alpha particles that were used to treat cancer of the retina. And so they would shoot the beam through the pupil of a person's eye and arrange the energy such that the range was just enough to get to the retina and deliver the dose there.
That's like super precise.
You betcha, you betcha. But with accelerator technology today, we can do that.
Wouldn't it be like millions of dollars to get a dose?
It's very expensive, absolutely right. And so, you have to get into these cost-benefit analyses and see if this is really the most efficient way to do that kind of treatment. But for a number of years, that was the only way that kind of cancer could be treated. And at the Bevatron, another large accelerator we used to have at LBL, they were using heavier ions to do the same thing. There's now a big accelerator down in Loma Linda, California, near LA, and they're using protons to do this kind of cancer therapy. For again the same reason, because of this Bragg peak, delivering the dose most effectively right where the tumor is. Sometimes these effects happen and they're not exactly what we want. I've mentioned a little bit about cosmic rays. So cosmic rays are radiation that come in from outer space, and they consist of all kinds of particles, electrons, muons, protons, and every atom from hydrogen up to uranium is a constituent in the cosmic rays. And they undergo the same kind of energy loss when they enter a material. So for example, if you have some kind of electronics, computer chips, or complicated electronics, occasionally a cosmic ray will go right through them. And the cosmic rays will lose energy in that material, and they can cause what are called single event upsets. So imagine you have a computer memory, which is nothing but a bunch of zeros and ones recorded magnetically. An ionizing radiation can come in and convert a 0 to a 1 or a 1 to a 0. That's called a single event upset. And this is a big problem, especially for electronics that are going to fly on spacecraft, where the cosmic ray flux is a lot higher than it is on Earth. And so when we go up to Lawrence Berkeley Lab, you'll see they have a whole cave, a whole experimental facility dedicated to allow chip testers to come and irradiate their chips with beams that mimic the cosmic rays. And the Air Force is currently buying 40% of all the beam time at the 88-inch cyclotron to allow this kind of chip testing to go along, so that before any electronics is allowed to fly on a U.S. spacecraft, it's been tested in a laboratory to ensure it's as radiation insensitive as possible. And so what these guys will do is they'll bring complicated electronics, wire them up, operate them, and then shoot the beam in and watch what happens as an event-by-event process happens in there. So I was mentioning that you don't have to use that complicated formula very often, except maybe once on your homework. Jim Ziegler has put together a very, very nice website where he has a program called SRIM. It's the Stopping and Range of Ions in Matter. And this program can be downloaded for free. You just click on here and it'll appear on your computer. And then you can use it to calculate energy loss and ranges of any ion in any material in a couple clicks. So this is a calculation I did a few months ago when we were getting ready to do an experiment at the cyclotron, and we were going to shoot a beam of protons into a target of rhodium. And I wanted to know how much energy the beam would lose as a function of distance. So I typed in that I wanted my ion to be hydrogen, I wanted the target to be rhodium. It knows the atomic number, it knows the density, and I say I wanted to calculate energy loss and range for a certain range of energies between 20 and 40 MeV. I push the button and out comes this output. And what it shows me is the energy loss, and I can pick whatever units I want here. The energy loss happens to be MeV per millimeter. So for every millimeter of rhodium the beam passes through, this is how much energy it's going to lose in MeV. And it also tells me the range, how far the beam would actually go before it comes to rest. So a 40 MeV proton in rhodium is going to go through 2.16 millimeters before it comes to rest. So that's a very useful website. I would suggest you check it out if you ever have to do any calculations involving energy losses or ranges in material, other than my homework. Okay, so I think we'll stop here for today and we'll pick up the discussion Wednesday. And please get me the emails with your nationalities.